Hello learners, welcome to this course on Embedded System Design using Raspberry Pi 4. In this tutorial, I will be describing about how to interface a Dotmatrix display with Raspberry Pi 4. So the complete project and its code is available in the GitHub repository link given below. Dotmatrix display. From the name itself, we can understand dot means LED. So we are going to have many dots and each dot is going to be an LED. For example, here I show a 8x8 display where we have lot of dots. So each dot is a LED. Matrix represents these LEDs are connected in a matrix fashion. So by activating a particular row and column, we can activate or deactivate an LED. So for example, here I show 8x8 display, which means I have 8 rows and 8 columns. To activate a particular LED, to switch on a particular LED, for example, I want this LED to be on. In that case, I have to activate this row and the corresponding column. So thereby I can make this LED to glow. So we have LEDs connected in a matrix fashion and it is used as a display. So display in the sense we can use it for displaying alphabets, numerals, symbols or even graphics like smiley, squares, circle, etc. So this dot matrix displays are low cost electronic digital display devices. And we can connect as many number of this dot matrix display together. I can put one more dot matrix display and another one. So thereby I can even display a big sentence on this dot matrix displays. So in this tutorial, I will be discussing about how to interface this with the Raspberry Pi 4 module. So as I said, this dot matrix display comprises of rows and columns. It comes in different sizes like 3x5, 5x7, 7x5, 5x9, 8x8, where one value represents a row, another value represents a column. So 8x8 in the sense I have 8 rows, 8 columns. If I have 8 rows, 8 columns, how many LEDs I can connect? I can connect 64 LEDs I can connect. We can able to make use of 64 LEDs in this dot matrix display. If I want to connect the 64 LEDs individually, then I require 64 GPIO lines. By using this LEDs in a matrix fashion, I am reducing the number of lines from 64 to only 16. So 8 pins for your row and 8 pins for your column. So only 16 pins are required. So thereby I can activate any LED out of the 64. Still, I want to reduce the number of pins. 16 is still a big number, right? So I can't use 16 GPIO pins for connecting one dot matrix LED. So still I need to have an improvement or reduce the number of GPIO lines. In that case, I am going to use an IC called as MAX7219 IC. So in this MAX7219 IC, it takes the data using SPI protocol. So SPI stands for Serial Peripheral Interface. It's a serial communication protocol. It's a serial communication protocol and it's a synchronous protocol. Synchronous protocol in the sense where the data will vary with respect to the clock signal. The speed of data transfer will be in relation to the clock signal. So it takes the data via SPI protocol and this data can be converted into corresponding row and column information by this IC. So I have SPI module in my Raspberry Pi. So we can make use of this SPI module, generate the signal, send it to my MAX7219 IC. This is one way. But what we are going to do here is, I am not going to use this hardware SPI. We are going to generate this SPI in a software mode. Software mode in the sense, using some GPIO lines, I am going to create this SPI signal. For SPI, we have 4 lines: MOSI, MISO, slave select, and clock signal. So MOSI stands for master output slave input. Who is master? The Raspberry Pi is your master. MAX 7219 IC is your slave. So for master it is output, and for slave it is input. So which is something like a transmitter line, right? So transmitter line from your Raspberry Pi. MISO is master input, slave output, which means now the MAX 7219 is going to transmit the data. But for our dot matrix display, we need only the data coming into the MAX 7219 IC. We need not send the data back to the Raspberry Pi, so we are not going to use this MISO line. So we are going to use only this MOSI line. And the slave select, or we can call it as a chip select. So we can use this line for selecting this IC. Then data transfer can happen. Then at what rate the data will be transmitted, it depends upon this clock signal. So we are going to make use of these 3 lines. GPIO 17 line will be acting like a MOSI line in SPI protocol. GPIO 18 line will act like a chip select line, and GPIO 27 line will act like a clock signal. So thereby we create a software SPI protocol. So this we call it as bit banging method. Once the data is transmitted to your MAX 7219 IC, this IC will generate the corresponding rows and columns. So thereby we can activate a particular LED in this dot matrix display. We will see how we are going to activate this dot matrix display. There are 2 ways in which we can activate this. For example, in a column, I can give a ground line. Right? So ground line in the sense this first column will be fully ground. Then what I can do, I can send a pattern here in this row. For example, I can give something like 0, 1, 0, 1, 0, 1, 0, 1, which means I am sending 5 volt to this LED, this LED, this LED, and this LED. I am sending 5 volt, which means this 4 LEDs will be on. Other 4 LEDs will be in off state. Same way, next what we will do is we will move this ground line to the second row. Again we will send some pattern here. So for example, I will give something like 1, 1, 1, 1, 0, 0, 0, 0. In that case, what will happen? This 4 LEDs will be on, this top 4 LEDs will be in off state. So like that we can switch over from one column to the next column, and we can send the corresponding data to your rows. Thereby a particular column will be highlighted. So you can see this animation right now. You can see at any time only one column is activated, right? So you can see it in a slow motion. You can see the variation. Only one column is activated. But if I increase the speed, what happens? If I increase the speed, if I increase the switchover very fastly, then what happens is it appears that all the columns are being activated, but it is not so. Since the switchover is very fast, it appears that all the columns are being activated, and we can able to see a particular character or symbol or numbers in a stationary form. If we look at it in a very slow way, at any time only one column gets activated. For example, in one column I have only 8 LEDs. Let us assume one LED consumes 40 milliampere of current. So 8 LEDs in the sense that 320 milliampere of current will alone be consumed by this dot matrix display. But the switchover is very fast. Since the switchover is very fast, it looks like the character appears to be stationary. So that is how we display the characters, alphabets, numbers and digits in this dot matrix display. Now let us look at this MAX 7219 IC. So in this MAX 7219 IC, you can see that we make use of these 3 lines create the SPI signal, give it to this D in clock and load signal, and this MAX 7219 IC, what it will do, it will generate this segment signals. Segment signals are nothing but the row signals. Digit signals are nothing but the column signals. And it will be given to your dot matrix display. Now let us look at the details of this MAX 7219 IC. So IC MAX 7219, it has internal control registers, and by using these registers we have to configure it properly, thereby we can get different functionality from this MAX 7219 IC. And remember, this IC can also be used for your 7-segment displays. We can use it for 7-segment display or for dot matrix display. And the communication to this IC is via SPA. And we will be transmitting 16-bit words, which means 2 bytes we will try to transmit. So 2 bytes, out of this 2 bytes, 1 byte will be register address, another byte will be your data. 1 byte will be a register address and another byte will be your data. So here this IC has 16 registers. So 16 registers in the sense its address starts from 0x00, it goes on till 0x0f. So 16 addresses are there. In each address I can put a data, and each data will have some specific functionality. For example, from address 01 to 8 represents the data for each row. When I activate a particular column, I have to send a value to a row. How many such rows I have to send? I have to send 8 rows I have to send, right, one by one. So those 8 row content can be stored in this 01 to 08. So where we have this data for each row in the dot matrix display. Next address is 0x09. It represents the decode mode. Decode mode in the sense it is used only in the 7-segment display, right? We are not going to use this decode mode, so we will set this address to be with 0x00 for dot matrix display. Next 0x0A address. It represents the intensity of the LED. So here I can change this value from 0x00 to 0x0f, which means 0x00 means dim. 0x0f means it will be brightest. The intensity of the LED can be varied. I can set any value between 0x00 to 0x0f. Next one is 0x0b address. So this represents the scan limit. Whether I want only the first column data or I want all the column data. If I put 0, only digit 0 is enabled. If I put 7, all digit 0 to digit 7 is enabled, which means column 1 to column 8 gets activated one by one. Then 0x0c represents the shutdown. Shutdown in the sense we can switch off the display by setting it to 0x00, or if I want a normal operation, we will set it to 0x01. If I want to test the dot matrix display, in that case I can make use of this address 0x0f. If I set this 0x0f to be 0x01, in that case all the LEDs will be on. If I don't want to test it, I can put it to 0x00. And this address 0x00 is used only when I am going to cascade multiple MAX 7219s. If I want to use more number of dot matrix display, in that case I have to use more number of MAX 7219s. In that case we will make use of this 0x00. So here I show a typical MAX 7219 IC, where this data in will come from your microcontroller, SPA signal, and this left side represents the column information. Then I have a chip select signal, clock signal, and here I have the row information, and we also have a I set. I set is an intensity set. This is a hardware based intensity setting. So here I can connect a potentiometer, and by varying the potentiometer content I can able to vary the intensity of the LED. Then we have a D out signal. So this D out can go into a D in of your next MAX IC. So thereby multiple dot matrix displays can be interfaced together. So now we are going to create concentric squares using the dot matrix displays. So concentric squares in the sense I am going to create a square, and inside that square I am going to have another square. So concentric squares we are going to create. So for this project we are going to make use of Proteus 8.13 professional software, and the language of programming is going to be Python. So we make use of a Raspberry Pi 4 module. We take this 3 lines. GPIO 17 is connected to D in, 18 is connected to chip select line, 27 is connected to clock line. And the intensity set, I am going to connect it to a 10K resistor and to a ground. So the data will be transferred from your Raspberry Pi module to your MAX 7219 IC, and it will generate the corresponding row information and column information. So this information will be fed to this dot matrix display. So thereby a particular alphabet, number, symbol or any graphics can be obtained. Let us look at the programming part. So first we import the necessary packages. We are going to make use of a GPIO. So we import the GPIO package. Then for delay function we import the time package. Then we assign the pins 17, 18 and 27 to variables D in, chip select and clock line. Then first I am going to set the mode, whether I am going to use a Raspberry Pi board pin or IC pin. Here I set it to be BCM, which means I am going to use a IC pin, BCM 2711 IC pins. So this is a ARM Cortex A72 processor. Then I am going to set this D in, CS and clock signal to be a output signals. Then I am going to define a function called pulse, where I will set this clock to be high for some 10 microsecond, and then it will go to low after 10 microsecond. So for that we define a function here. So the pin will be 1 for 10 microsecond and then it will go to low. Then we define a function for sending a byte, because I have to send 2 things. One is address I have to send, another one is data. Both are 8 bits, right? So address is also 8 bit and data is also 8 bit. So this I have to send. So for that I define this function. So we take either address or data here. Using a for loop, I am going to take one by one bit by bit, and then send it to this D in pin. Right? For example, let us take, I am going to send the address of 0x0, let us take 3, right? Which means I can represent it as 00000011. So this I am going to AND it with 10000000. So this is 0x80, right? So when I do AND operation, so I am taking this MSB bit which is 0. So this is being transferred to your D in when the for loop runs for the first time, right? So then I am generating this clock signal. So clock signal goes from high to low, right? Then what I am doing, I am trying to shift the data. So now this data is shifted. So shift the data in the sense, now this bit will come to this position and this bit will be assigned to D in, and again I will generate the clock signal. Again next for loop sequence, this bit will come to D in, again I will do this. So like that I am going to do it for 8 bits. So one by one I am going to send the data. So next function which we are going to define here is to send the register address as well as data. So address is given here, data is given here. So first I will enable the chip select. So chip select will be enabled when I give a low signal. Then I am sending the address information. Then I am sending the data. So altogether I am giving 8 bit, 8 bit. So total 16 bit information I am sending. Then afterwards I am making the chip select to be high, which means I am deactivating the chip. Then I am going to initialize the MAX 7219. So first address 0x09, I am going to send 0x00. So 0x09 represents the decode mode, As I said, decode mode can be used for your 7-segment display, not for your dot matrix. So if I want to use it for dot matrix, we set the value to be 0x00. Next, 0x0a represents the intensity value. So this can vary from 0x00 to 0x0f. If I put 0x00, then LED brightness will be very dim. If I put 0x0f, then it will be brighter. So I am going to set an intermediate value 0x05. Next, 0x0b represents the scan limit, whether I want the first column alone or all the columns. So if I want all the columns, then I have to set the value to be 0x07. Then 0x0c represents the shutdown. So I want a normal operation, so I send the value of 0x01. Then 0f location represents whether I want to test my display or not, whether it is working or not. I don't want to test it, so I set a value of 0x00. So this is the initialization part. Same way, I need to initialize the locations. So the locations, 8 bytes I am going to save. From where? From 0x01 location to 0x08 location, 8 bytes. So row 1 information, row 2 information. So like that, row 8 information. So this I am going to initialize. So for this, what I am going to do, I am going to take I varying from 1 to 8. So 1 to 8 for each location. For one location, I am going to set it with 0, 0. So row 1 will be set with 0x00. Next, I value will change to 2. So next location, again 0x00. So like this, I am going to continue till all the 8 bytes have been initialized with 0x00. So that is what we do in this DEF function. Next, we are going to write a function for displaying a pattern. So as I said, pattern, I am going to display concentric squares. So concentric squares in the sense, so this is a 8 by 8 matrix. So wherever I have 1, this corresponding LEDs is going to be on. 1 means on. 0 represents off. So you can see that the outer LEDs are going to be on. Same way, there is another square where I have LEDs to be on. So 2 concentric squares I am going to generate. To generate this pattern, I want to have a values for the rows, right? So how to get these values for the rows? So this is the first column, and for first row, what is the value? It is 0xff. Next value is 0x81. Next one is BD. BD in the sense 1011. So this is your B. 1101 is your D. So like this, I am going to take the values depending upon the what pattern you want. So those patterns we are going to initialize here. Those pattern we are going to initialize here. FF 81, BD, A5, A5, BD 81, FF. Then one in a for loop, 1 by 1 I am going to take. So in the first location, what I am going to do, I am going to take pattern of 0. So pattern of 0 is what? FF. So FF will be going to this 0x01 location. When the for loop runs for the next time, 0x02, what will be the pattern? It will be 81 will be going here. Same way for the last pattern, 0x08 location, I will get this FF going to that location. Then we define a main program here. So I want my embedded system to be running continuously. So while true always, we initialize the 7219 IC, clear the display pattern, then show the display pattern. So this pattern will be displayed for 5 seconds. After 5 seconds, I am clearing the display. Then clean up the GPIO lines. Then I am going to call this main function using this code. Now let us look at the simulation part. So here we use a Proteus 8.13 professional software. We take a Raspberry Pi 4 and we use this 17, 18 and 27 connected to your D-in, load and clock signal. So the data is transferred to this MAX 7219 in a software SPI mode, and this MAX 7219 generates the row and column information. Thereby we get the pattern here. Then we have a source code available here. So the program which I explained earlier is given here. We import the packages, define the pins, set the pin to be an output. Then we write a function for creating a pulse, sending a byte, sending the values, both address and data. Then initialize the MAC 7219 IC, clear the values for the pattern, then define a pattern information. Then using a main function, we call these functions and we execute the code. So after writing a code, compile the code, then go to the schematic capture, run the program. You can see 2 concentric squares gets displayed on the dot matrix display. So this is how we interface a dot matrix display with Raspberry Pi 4 module. Thanks for watching. Please like and subscribe for more technical learning. The complete project code and simulation is available in the GitHub repository link given below. Thank you.